on the last class, so I'm doing actually better this time around. I don't have that much. This shouldn't take us the whole period. So just as a quick recap here, I love this topic of looking at non-equivalent colorings of some physical object. This is going to be an object we denote with omega. It's a geometric figure. It could be two-dimensional or it could be three-dimensional, right? In theory, it could be higher than that. And we have two things that we're kind of playing with here. There is a group of symmetries of that figure. Okay, so that would be things that you could do to the figure that would leave it unchanged. Now, so far, the main example of that I've used is the idea of the symmetries of a necklace. So I've talked about taking a necklace and rotating it, or maybe flipping it over. And so we get this dihedral group it's DN. The one that's on this handout is specifically D4. But we have these rotations and reflections of this figure. I just want to be clear, you don't always have all of those symmetries. Instead of a necklace, what if it was a merry-go-round? And I bring this up because it's going to be on the group work. You can imagine rotating a merry-go-round and saying, well, if I rotate the merry-go-round by 1/n of the way around, that would be a symmetry of that merry-go-round. But you're probably not thinking that you're taking this merry-go-round and tipping it upside down, flipping it over the way you would for a necklace. So the group of symmetries is something that is maybe not always obvious. It might depend on what the objects were. So if these are horses on a merry-go-round that are supposed to be upright, you would not flip them over and have upside down horses on that merry-go-round. But you could flip a necklace over and that you wouldn't even think twice about that. So you have to just be a little clear about that. But there's a group of symmetries. We're going to call it G. And then we have the colorings of this figure, which is this script C. And in this context, guys, we're basically allowing each vertex to be colored any color that we want. So you remember earlier we had these rules that, oh, well, two adjacent vertices can't be the same color. We're kind of, giving that up right here. So like yesterday or on Tuesday, I guess it was, we were drawing these squares and we had things like this, blue, 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 yellow. And of course, the blues are next to each other. This would not have been an allowed coloring in the technical sense of how we defined colorings in the first place. But now we're in a new chapter and we have new rules, and our necklace can have adjacent beads that are the same color. That would be a reasonable thing to have, so we don't want to exclude that possibility. But what we're going to do is create a vector that consists of the colors of those vertices. So we have to sort of identify, like maybe this is vertex 1, vertex 2, vertex 3, and vertex 4. And so this coloring would just be blue, 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 yellow, like that. Okay, in that order, the way I've set up those corners of that square. Okay, so we can look at that. Now, I made a note on Tuesday, just to remind you here, two colorings, that would be two vectors, C1 and C2, they are equivalent to each other if and only if we can find some symmetry in our group that would take us from one coloring to another. Right. So in the case of the one that I have on the board here, we drew these already on Tuesday, so I won't dwell on drawing all of the examples out, but we can rotate this square by 90 degrees clockwise, or even 180 degrees, or 270 degrees, right? We could do any of these things, and these are all equivalent to the original coloring on the far left. So I'm just drawing a bunch of equivalent necklaces here that look like that. Or we could flip. I guess there's one more, isn't there? We could flip along the diagonal. I guess it's the tau 1, which goes diagonally from the upper left to the lower right. If I flip along that axis, actually, when I do that, I end up getting this picture again. Yeah, of course, it's already there. So I don't need to draw anything else. Those are all of the configurations that I could have. So all of these are equivalent to each other. I can get from one to the other through the use of one of these symmetries on this handout. Okay? And then we developed this notation that if we fix a coloring, C, we can talk about the stabilizer of that coloring. That would be all of these symmetries F, such that F fixes the coloring C. So F star C is equal to C. This is called the stabilizer of that coloring. It is actually a subgroup. I wrote the word subgroup. For those of you who've taken modern algebra, you're probably familiar with the less than or equal to notation that's usually used for subgroups. It's a subgroup of all of the symmetries. Yeah. So you have the stabilizer of any coloring. All right. So on this example here, we did some examples already the other day, but let's just review this one that's on the board already. The stabilizer of this coloring blue, 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 yellow is just like which of the, elements from the group will leave these colors exactly where they are. And I think we did this probably already on Tuesday. The identity element is always going to be in the stabilizer, right? Because you pick up the square and set it right back down the same way. And the other one would be actually reflecting across this axis, doesn't move any colors to different places, and that is the tau 2. Right, so you'd have that as an example. Okay, so anyway, that's just another example for us to have in mind. Given a coloring, we can calculate the stabilizer of it. Conversely, we could start by fixing one of the symmetries, so some little f from the group of symmetries, and calculate script C of F, which doesn't have a better name. We need to come up with a name, guys. Colorizer? I don't know. There'll be some word that we could make. It's the set of colorings that that particular symmetry fixes. Yeah, so notice it's the same condition. It's just a matter of your perspective. Are you fixing the coloring and finding the F, or are you fixing the F and finding the colorings? It goes kind of in both directions that way. Okay, so all of that we set up last time, and then we even got a little bit further into it. I wrote down a theorem and proved it. I'm going to state the theorem over here one more time for us. It's theorem 14.2.1. And what this says is let C, vector C, be a coloring. So it is in the script C set. And then we're going to let F and G be from the group of symmetries. And then the statement here is that F star C is the same as G star C if and only if the composition of F inverse composed with G is actually in the stabilizer of C. So that's the statement of our theorem. Okay. On the surface of it, if I start with a coloring and I ask you, well, how many colorings are equivalent to it? I'm still saying equivalent. We'll get to non-equivalent later. For now, equivalent. Your first reaction to how many colorings would be equivalent to C1, your first reaction might be, oh, well, every time I change my F, I would get a new coloring associated with that symmetry. And your first reaction, which turns out not to be correct, might be, oh, well, the number of colorings equivalent to C1 will just be as big as the size of the group, because every element of the group can be starred onto that coloring, right? But what this theorem is actually saying is, no, 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 it is possible that more than one of your group elements could produce the same resulting coloring, right? So that you're not getting that many different colorings. Okay, so I mean, you might think, yeah, oh, if I just take every element in the group and star it onto C1, how many things will that be? Well, that would be one for every group element, except that it doesn't work that way. This theorem says it's possible for two different group elements to actually give you the same result. You've duplicated the same coloring. And that means you would have less colorings at the end of the day that are equivalent to what you started with. Does this make sense? Yeah, so in fact, we can maybe put a little remark here. I proved this last time, so I won't prove it again right now, but I do want to make sure we understand what this is telling us. So I'll add a little bit of a remark here. For a fixed little f in the group. So if I have a particular symmetry that I'm going to apply to C, then there are order of the stabilizer of C choices for a group element little g in G such that F inverse composed with G is in the stabilizer of C. Right? So, if, let's just make up a number. If the size of the stabilizer was 10, you have 10 different elements here, and you've got this F in your hands already. The question is, how many things could you multiply the F by to make sure that you land inside this stabilizer? Well, there would be as many choices for G as there are different results in the, you've got 10 dots over here. Right, you got 10 different elements, right? And you've got this F inverse that's going to be composed with potentially anything and has to land on one of these dots, right? So you've got 10 arrows that you could make depending on what you put into that box, if I'm making any sense. Right, so the point is that there are, however big that stabilizer is, that's how many different G's you would have that would make this true, which isn't just another way of saying that's how many different G's would result in the same coloring coming out of applying it to C, right? Because this is just restating what's in the box. Right, so we're getting a little bit of a sense of the fact that the number of different colorings that we can make starting from C isn't as big as we thought. Right? You start with C and you try to star it with elements of the group. Well, you don't end up getting as many things as you thought, because a lot of times F star C and G star C are the same. They're the same basically just as often as you can choose a G that creates F inverse G inside of the stabilizer, and there would be order of the stabilizer many of those. You guys with me? Okay, so then here's a question. Get a better marker here. Let's see if this looks better. This is all, yeah. Question. Given a coloring, this is better. Given a coloring C, here's the question. What is the size of the set of the F star C's that we could get, where F runs through the entire group of symmetries? So given a coloring, how many different colorings can I achieve by applying some group element to it? This is just another way of saying, i.e., how many colorings are equivalent to C. Just another sort of, in words, a way of expressing the same question. How many colorings are equivalent to C? Because that's what equivalent colorings look like. Equivalent coloring, the equivalent colorings to C look like F star C. So the question is, how many different results can you get out of that? Well, the next corollary answers that. Okay, so we're going to answer this question in corollary 14.2.2, and you are probably not going to be surprised by the answer. The sort of obvious answer that you would like to be true is that the answer is the size of the group G. But as I've been saying, it's actually not that big because a lot of times these are duplicating. So what is the right answer? Let's get this down. So let's let C be a coloring. The number of different colorings, notice I'm saying different, the number of different colorings equivalent to C is, so it's the size of this set that we just wrote down. So I'll just recopy it again. So this is the notation. It's just the size of that set. And what is it equal to? Well, this is the formula. It is not the order of G, but it is the order of G divided by the order of the stabilizer of C, as it turns out. That turns out to be the right answer. That turns out to be the right answer. So it's less than the size of the group. And that's kind of because, like, if you're familiar with like modular arithmetic, you're sort of collapsing together, like you're taking all of the group elements, but you're putting them into piles that each have size stabilizer of C. And each pile creates only one sort of coloring. It's associated with one coloring. So the total number of colorings that you get is cut down by that factor, right? By the way, if you just look at our example over here, does it work? For our example, if we take our coloring of blue, 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 yellow from above. So the size of the stabilizer, it looks like we already calculated this, didn't we? The stabilizer had 2 elements in it, right? That was 2. And of course, the size of my group, this is just the dihedral group, so there's 8 different symmetries of my square. And so according to this formula, the size of G divided by the size of the stabilizer of C would simply be 8/2, which is 4. And yes, indeed, there are 4 colorings of this figure that are equivalent to the one that we started with. Those are the 4 pictures that are on the board here. Okay, so that's what we end up with. We don't get 8 different ways of coloring the square. We only get 4. That's because more than one of these group symmetries has the same effect on this necklace. It's the same effect on this necklace if I pick it up and set it right back down as if I decide to flip it across this axis. Those are 2 different symmetries, but they both give us the exact same color. So the size of our set of equivalent colorings is smaller than expected. By the way, don't forget that this size of the stabilizer always divides the size of a group. I mentioned Lagrange's theorem from group theory on Tuesday. So the stabilizer is a subgroup of G. So this is not going to give us a problem. We're not going to get like some fraction over here. This has to be a whole number, of course. And it will be. It absolutely will be. Okay, so that is the corollary. But we are still talking about how many colorings are equivalent to C. Whereas the real question that the 10-year-old is going to ask you is, well, how many non-equivalent necklaces can I make out of, you know, 3 blue beads and 1 yellow bead or something like that? How many non-equivalent necklaces could I make given certain conditions? So that is something we haven't talked about yet, and I'm going to do it right now. It's a theorem that is pretty much the famous theorem on this topic. It is Burnside's theorem. In the book, it is theorem 14.2.3. And this is due to Burnside. Actually, it is sometimes known as Burnside's lemma. And so be a little bit careful. This result that I'm about to write down is actually not his most famous result. So this guy was around from the late 1700s to the mid 1800s, and he was actually an expert on finite group theory, which is what I love to talk about. His most famous theorem is that if you take any finite group whose order, we don't need to know this for this class, it's just extra information. If we take any group whose prime factorization involves just powers of 2 primes, that any such group is always solvable. And solvable is a word you may learn in 407 if you, well, if you take it with me, you'll definitely learn it, but I don't know if they all go over this topic. It has to do with, so it turns out that to any polynomial, you're trying to see whether it's solvable by radicals. That is, can you write a formula for its roots just using addition, subtraction, multiplication, division, and extraction of roots? And some polynomials you can, and some polynomials you can't. What you can do, what you learn in 407, is that you can take a polynomial and associate a group to it. And if that group is solvable, whatever that means, then that particular polynomial will have roots that can be expressed using addition, subtraction, multiplication, division, and extraction of roots on the coefficients of that polynomial. So it's sometimes yes, sometimes no. It depends on the polynomial a little bit. At any rate, this is way past what we need to worry about for this class, but just so you know, he is much more famous for his work in group theory, but he is credited with this result, and it's sometimes called Burnside's lemma. And here is what it says. So now let's get back to the notes here. The number, and I'm going to denote this as n of g comma c, just to be consistent with the book's notation. The number of non-equivalent colorings of omega is, so now we're getting to it. We're getting to the thing we really want to be able to do, which is to count non-equivalent colorings. And here is the formula. We're going to divide, it's a big fraction. The bottom of it has the size of the group on it, okay? And in the numerator, we are going to do a summation. And this is a summation over every element of the symmetry group. So this is the set of, or sorry, the summation over every F in the group of the size of script C of F. That's what it is. That's the whole thing. So that's the theorem, the Burnside's theorem. So if you know how to calculate script C of F, you're going to have good luck with this formula. You're going to be able to calculate things using this formula. You know, we should do an example. We also have to do the proof. I don't know which one you want to do first. The proof?
We'll example one. We'll get it.
You want the example first? Okay, we'll do an example first. I don't care. So I'll do an example. Well, let's just do the one that I've been working with already since Tuesday. The colorings of the square using blue and yellow, right? So how many non-equivalent colorings of a square using blue / yellow are there? Yeah, this would be a good one because we have a lot of the information already at our fingertips. So what you're going to do is basically calculate n of g comma c. What is my group of symmetries for this square going to be?
The D4.
It's right here. Yep, it's the one we've been looking at. And how big is that group?
I think there's 8.
8 different elements, aren't there? Yeah, there's 8 elements to this. And so that means that my numerator is a sum of 8 terms. So we can start thinking about like what would be C of some of these possible elements. Starting, I always like to start with the identity element because it's kind of an easy one. So what is the C of? We need to remember what this was. This was in the recap already. The C of F. This is just the set of colorings such that F star C is equal to C. Well, if you use the identity element fixes every coloring. So all I'm really asking you for here is how many total colorings would there be of the square using blues and yellows? 4 to the 4.
Yeah.
5. 2 to the 4.
2.
2 choices for each corner, right? Blue or yellow, blue or yellow, blue or yellow, blue or yellow, 2 to the 4th. Yeah, so this is just 2 to the 4th. Okay, does that make some sense? Every single every single coloring is fixed by the identity. And I'm looking at 4 dots. Right, I'm looking at 4 dots. Another way to think about it, guys, is you're creating a vector here that has 4 entries. C of 1, C of 2, C of 3, and C of 4. And it's an ordered vector. There's a first vector, second vector, third vector, fourth vector. Sorry, first vertex, second vertex, third vertex, fourth vertex, and they each have 2 choices. Blue or yellow, blue or yellow, blue or yellow, blue or yellow. That's 2 to the 4th choices. Okay? So this one is actually 16. Okay, let's do one that's a little more interesting. Let's do the row 4. So I'm using this handout. Does anybody need this handout still? Yeah, I got extras. Yeah, it's also online. So anybody else? Okay, so row 4. This is the 90-degree rotation. So my question would be, how many colorings would remain unchanged if I just rotate by 90 degrees? In other words, your vector cannot change. What do you guys think?
With 2 colorings where they're all the same color.
They could all be blue. So if every vertex is blue, that's going to be fixed by a 90-degree rotation. And if every vertex is yellow, that's going to be fixed by a 90-degree rotation. Or would there be any others that have a mixture of blue and yellow that would be fixed, that would stay the same when I rotate 90 degrees?
No.
I don't think so. You try something like, blue, yellow, blue, blue. If you rotate this by 90 degrees, it won't look the same anymore, right? Because the yellow gets moved. And so, yeah, there's nothing else. It's just 2. It's just 2. The all blue coloring, and so sorry, these should be sizes actually. I'm talking about the sizes of these sets. That would just be 2 as well. Okay, let's do the 180-degree rotation. Row 4 squared.
4.
Yeah, this one's a little harder. So I have to ask myself, which colorings would be unchanged if I rotated by 90 degrees? Well, what you can do is you can pick a starting corner and then say, well, after I rotate that by 180 degrees, the resulting corner needs to be the same color for it to stay unchanged. But notice that the other 2 corners are not affected by that choice. So if I've chosen blue here, and I therefore have to choose blue there, but this other vertex could be either color. I could choose blue again, or I could go to yellow, in which case that has to be yellow. But I have two choices here and two choices here. The rest of them will then be dictated. So would everybody be comfortable if I said that was 2 squared?
Yeah.
Yeah, that's gonna be 2 squared. The next one is the 270-degree rotation. I'm kind of going in order on the handout here, doing all the rotations first. A 270-degree rotation is no
Same
different
as
than a
90.
90-degree rotation. It's just turning it the opposite direction, so you're back to 2 choices again for that. Right, see, the guys, the idea is this. And I'm not trying to say I mean, maybe you guys are all getting it already, I just wanna be explaining it as many ways as I can. Imagine that you colored this upper corner with blue paint, and then you rotate it by 90 degrees. You can't help but get some of that paint onto this corner. And you can't help but get more of that paint onto this corner. It keeps getting transferred around to all the vertices. So on a 90-degree rotation, either clockwise or counterclockwise, once you've colored one of the corners, that corner will then, whatever paint you have there, will then be moving around to each vertex. And therefore, those other vertices are all the same color. Is that making sense? Whereas if I go 180 degrees, whatever paint you use in the upper left corner will only get transferred to the lower right corner. It won't affect the other two corners. So I have a whole new fresh choice I can make. Okay, let's get to the reflections. First we have the diagonal reflections here. And I'm curious if anybody has an idea for how many different colorings would be fixed by reflecting across this axis. Whatever color I choose here has to be also chosen here. So I have 2 choices collectively for those 2 vertices, just 2.
And then the other ones have 2 choices.
But the others can be anything,
So
because the other vertices don't move.
that would be 8.
So that's actually 2 cubed. Yeah, this is actually 2 cubed for the tau 1. You guys buying that? If I put a color here and I put a color here, they can be independent of everything else. Whatever color I choose here must also be used over here. Yeah.
When you like pick this vertex and then you like do the action of the
Yes.
thing on it, do you have to repeat that until you get back where you started, or is it just one?
You can and should repeat it, because if I'm asking where does the paint that was on this corner end up moving to, and I say, well, it moves over here, but then this corner is moving somewhere also. So it's like, well, where would that one go? Well, that would go back here. So these two are transferring paint between each other. And so, yeah, and if you were doing the 90-degree rotation, yeah, as soon as I move the blue from there to there, then I want to know, well, the blue that was here, where does it go? It goes there. And so, you are kind of looking at all of the vertices as if you've applied multiple operations. Yeah. The tau 2 is going to be the same. What about the tau 3? I take my square and I flip it vertically. How many colorings would be fixed by this vertical flip?
2. So you only have 2 choices.
I have 2 choices here, blue or yellow, right? But whatever I choose there, I have no choice over here. It has to be the same, right? Same thing here, I can do blue or yellow here, but then it dictates that on the other side, I have to use the same color again. So it's 2 squared, right? And then the very last reflection is the horizontal axis, and that will be the same as the vertical axis. Okay, so let's see. 16 plus 2 is 18, plus 4 is 22, 24, 32, 40, 44, 48 over 8, which is equal to 6. That's the answer we got by drawing them all out on Tuesday. So on Tuesday, we drew out all 6 non-equivalent colors. Okay.
Whenever you have a fixed like force position,
Mhm.
the number of choices decreases by versus decreases by 1. So
Right.
So that's what for the third one, right?
I'm talking about for this.
Choose the third, right? The first one.
The first two, the third, that.
Oh, this one?
Yeah.
Oh, so this picture here. Yeah,
Just recapping,
Which
right?
was Tau one.
That would force
Tau
you to-
one, yeah.
Tau one or Tau two.
Once you pick it, it forces one, so you're the amount of vertices you could use.
Yeah, this color here dictates what this color is because of
Yeah.
the axis of symmetry. So you only get one choice for that pair of vertices. You getting it? They have to be the same. The other two can be whatever, independently of that. Okay, so I don't know if you guys know this yet, but about an hour before class, I remembered something. I did this Burnside theorem on a Rubik's Cube. It's actually a three-dimensional problem, and I made a video for it. So I hope you won't mind. I added it to the homework for Sunday to just watch the video. It's about 17 minutes. It's interesting because there's actually a pretty big group of symmetries of a cube, right? So, and there are different kinds of things you can do. You can like spin the cube this way, or different axes you can kind of rotate it on. So I love for you to watch that, and I'd love to get your opinion of the video. Click the like button if it's good. But anyway, it's not that long. I think it would be nice. I mean, it's unlikely I would give you a 3D example on your final, but it's nice to know that you can use it.
Unlikely.
Unlikely. If I show up on Tuesday with a whole bunch of dice and big objects to pass out, you're in trouble. No, I don't think I'll do that. Yes, you need to use these dice to figure this out. Oh my gosh. Well, get myself in. Okay. Anyway, so does everybody kind of get how the theorem works? It's not so hard, actually. It's pretty nice. Let's do the proof of the theorem, and then you guys can decide. This is one of the theorems on the list. So if you like this proof, you can think about adding it to your list that you're going to reproduce for me in the next few days. I think it's a really nice proof. I really like this proof. In part because it's kind of got a flavor of a combinatorial proof to it, which goes back to something that we have talked about. So let's do the proof of the Burnside theorem, and I will get your opinion. You guys are the ultimate judge of whether you like this proof or not, but I think it's pretty nice. So let's do this. For the proof of that formula, we're proving, let me get everything out of the way here. We're going to prove this one right here. Okay, so here's how we're going to do this. We are going to consider the set consisting of a pair of things, a symmetry and a coloring. A symmetry, little f, comma, a coloring, little c, and this is such that F is in the group of symmetries, C is in the set, the set of colorings, and there's one more very important condition, which is that F star C needs to be equal to C. So we're not looking at all possible ways of putting a group element and a coloring together. We're only pairing them up in the case when the symmetry fixes the coloring. And what I'm going to do is count the size of this set. So we will count the size of this set in two ways. We're going to do it in two ways, all right? So what are the two ways that we're going to do? Well, that's what I mean. It's kind of a combinatorial proof. You sort of have a first way and then a second way, and then they have to actually really count the same thing. So method number one, the first way I want us to do this is for each fixed F in the group G. So we're picking some F here. What we're going to do is we count the colorings. We count the colorings C fixed by F. We're just going to count those. And by definition, there are How many colorings are there that are like that? Well, isn't that just the size of the script C of F? I don't have the definition of the script C of F anymore, but it's the colorings that are fixed by F. So the size of that, well, that would be the number of colorings that are fixed by F. So there are that many of them. So for each fixed F, we're gonna find this number, and then we're gonna add that up over all of the Fs. So summing over all little f's in G gives us, well, I'm actually going to write it as a summation of F running over the elements of G of the size of script C of F. That's what we actually have there. Okay, sweet. So that's method number one. That's method number one. And notice that what we got for an answer is certainly relevant to our Burnside theorem. We see it in the Burnside theorem. Is everybody following this so far? I want you to follow. I want somebody to do this proof, because then I get to grade it, and I like this proof. So it'd be a good one. Somebody should do this one. So I'm trying to sell it to you.
First line is not selling it.
The first line, oh, we will count the size of the set in two.
No, the bracket part.
Oh, consider that
The
whole
set,
set? Oh, you
yeah.
don't like that? Oh, that's not so bad. Yeah, just grab a symmetry, grab a coloring, assume that the symmetry fixes that coloring. Yeah, you do have to get that set written down correctly. There's no doubt about that. Okay, let's go to method number two. Let's go to method number two. Whatever this method number two is, should give me something that of course will be equal to this, because we're counting the same thing. This is a combinatorial proof, guys. We're counting the same thing in two different ways. We're counting how many of these can we make? How many times can I put a symmetry and a coloring together where the symmetry fixes that coloring? So this is one way of looking at it. Okay, this is one way of looking at it. Well, the other way of looking at it is, of course, to just reverse it all. Instead of fixing the F, let's fix the C and then look at which F's would fix that particular coloring. So for each fixed coloring C in the set of colorings, we count the number of symmetries F from the group of symmetries that fix C. That's what we're going to do. And we already know what that is. That's actually the size of the stabilizer of that coloring. Okay, so the stabilizer of the coloring, that's just all of the symmetries that fix that coloring. And again, we will do a summation over all possible colorings this time. So let's just try to get the language exactly the same. Summing over all colorings C in script C gives the summation, this time where C is in the set of colorings, of the sizes of the stabilizers of all of those colorings. So that is what we would have this time around. Okay. So far, so good? Now, I don't see the stabilizer in the proof over there, or in the statement of the theorem. So somehow we've got to do some more work here to get where we're going. But the point is that this number is equal to this number, because it's two methods for counting the same thing, yeah? They're the same. So let's just start from there. So we have, now I'm ready to give you the real lowdown on the proof. The summation over F in G of the size of the C of F is equal to the summation over the C in script C of the size of the stabilizer of C. And if you want to have a little justification here, this would just be since methods 1 and 2 count the same thing. Okay, so since the two methods count the same thing, then they have to add up to the same result. Okay. But now I'm going to work on the size of the stabilizer. And so this is the summation over all of the colorings C, such that, now do you remember from our corollary, just from a few minutes ago, the corollary 14.2.2 had the size of the stabilizer in it. You guys see that?
Yep.
Yeah, so you've got, the size of the set of F star C, right? Such that F is in G. So we wrote this down just a few minutes ago. This is the size of G divided by the size of G of C. I am going to solve for the size of G of C and stick it in on that summation.
Well,
So if I do that, it will be the size of G on top, and on the bottom, the size of the set of F star C such that F is in G. That's what we would have. And so this is by corollary 14.2.2. Now, if I actually solve for this numerator here, if I solve for what's on top of this fraction, I can see that the size of G should be one of the factors. And I'm now starting to get that. This size of G is a constant that can be pulled out of the summation. So I'm going to do that. I'm going to pull the size of G out of the summation completely, leaving me with just the summation over the colorings C of 1 over the size of the set of F star C such that F is in G. Okay. And now I'm going to rewrite that again. So that is equal to, so that step doesn't need any justification. I'm just pulling the constant value out. And I'm going to rewrite this one more time. 1 over, and now I'm actually going to think about what this denominator is. This denominator is actually just counting the colorings that are equivalent to C. So how do you find the colorings that are equivalent to C? You take every symmetry and apply it to the coloring, and you see how many different things you can get. So this denominator in words, I'm actually going to write it in words. It is the number of colorings. Sorry for writing so low on the board here, guys. Stretch your necks if you have to. It is the number of colorings equivalent to C. Sorry about that. It's a little hard to read probably, but I hope that's doable from where you're sitting. Okay. So, by the way, guys, we're almost done with the proof. We're almost done with the proof. If I can just convince you. Why are you laughing? You don't think I can convince you? I haven't even said what I'm going to convince you of yet. Just trust me. It works out. I'm going to convince you that this summation is the n of G comma C. This summation is the n of G comma C. If I'm right, If I'm right, then I'm multiplying it by the size of G and getting the numerator of that fraction. So if I can convince you that this summation adds up the number of non-equivalent colorings of my figure, then I'm good to go. Agreed? So can I convince you? I think I can. I'm gonna show you with an example for a minute. And then I'll come back to the proof. Let's just kind of go off on the side here and look at the example. You guys remember? I'm just gonna use the same example. This is not proof by example. This is just showing you kind of how this works. Remember our coloring of our square here, right? With blue, 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 yellow. So that'll be one of the colorings in this summation. And so associated with that picture, I will have a 1 over however many colorings are equivalent to it. Does anybody remember how many colorings are going to be equivalent to this one? We had it on the board a little bit ago. I circled them. The number of colorings equivalent were? That's not 2. It's 4. It's 4. I can take this thing and move the yellow to any corner, right? So there's 4 colorings that are equivalent to this one. In fact, if we wanted to write them all down, again, you don't need to. You've already got this in your notes, but because I like to wave my hands, I like to get all the pictures here. Any one of these things I'm drawing, guys, is equivalent to the first one. I'm just moving my yellow to a different corner every time. Starting from here, I can get to any of these, right? So if this is 4 colorings equivalent to C, that means that this particular picture contributes a 1 over 4 to the summation. Right? However, later on in my summation, this coloring will show up. Because it's a different coloring than this. It might be equivalent. It's equivalent, but it's not the same coloring. This is a different coloring of the picture. And how many colorings are going to be equivalent to this one?
4.
4. So this is going to contribute a 1/4 as well, right? And this one's going to contribute a 1/4 as well. And this one's going to contribute a 1/4 as well. If I add up 1/4, 1/4, 1/4, and 1/4, it's a total of 1. It gives me 1 term out of, those 4 colorings contribute a +1 to my total sum. And sure enough, this whole group is going to be one of my non-equivalent colorings. Remember, there are 6 of them. We calculated earlier, there are 6 of them. This is one of them. And we're getting it as a 1/4 plus 1/4 plus 1/4 plus 1/4. You with me? So what we can actually do, guys, is as we're adding up as we're doing the summation over these colorings, we can take all of the colorings that are equivalent to each other and kind of put them together as a batch. And if there's K colorings that are all equivalent to each other, then they're all going to contribute a 1 over K. There's K of them. So adding up 1 over K times gives me 1. So each batch of colorings that we're grouping up, and they're different size batches, but each batch is going to give me 1 on that summation. So the question is, what's the total amount you're going to get? Well, you're going to get 1 for every non-equivalent coloring that there is. That's the reason. So I have a bit of a write-up for this. I just want to explain it over here. So I'm just going to write down what I just said. Okay. So if we gather together all colorings equivalent to a particular vector C. If we gather together all colorings that are equivalent to a particular C when performing this summation, so this is where the explanation is. This is the part maybe I don't know if you like this or not, but you have to kind of figure out how to make sure you understand this little write-up. So if we gather together all of the colorings that are equivalent to a particular C, as we're doing this summation, then each equivalence class, it's really what we're talking about. Each equivalence class, like these 4 necklaces, they're all one equivalence class. They're just equivalent to each other. So each equivalence class contributes +1. I'll put that in quotes. It contributes +1 to the value of the total summation. So each equivalence class gives us 1 more in our total sum. But it comes in the form of 1 over k, 1 over k, 1 over k, 1 over k, k times. In this case, 1/4, 1/4, 1/4, 1/4. 4 times, that adds up to 1. So you're really just saying that this summation counts the number of equivalence classes, which is the number of different non-equivalent colorings that you could have. So thus, our last expression equals the size of G, which was out in front of the summation, multiplied by the n of G comma C. And that is the proof. That is the whole proof. What do you think? Does this make any sense? That's the whole proof. The last thing would be to just solve for the NG of C, but we don't need to do that. So just this summation, which is the numerator, agrees with the product of the size of the group and the number of non-equivalent colorings. Really pretty neat, pretty neat. There's a little bit of a combinatorial flair to that. So get some practice with that as well. Awesome, awesome. How is my mind coming along? Usually, not too good. Guys, I have a handout. Send this around. Any questions on that proof though? Somebody's gonna do this one, right? You guys are gonna have to like bargain with each other. Figure out who's gonna be the Paul guy.
Right on Kevin.
This guy? Okay. I'll sign him. I'll sign that. There you go, that's right.
What you look for now?
Yeah, some of you are gonna take another class with me. Pretty sure you're gonna keep me in your good graces. I just play with you. Guys, we only have 5 minutes. It's a little bit of short timing to maybe go through all of this group work. So can I just leave this with you and maybe we could look at this during the review session, I think. Or you can just try it on your own. These are not difficult. It's just applying the Burnside theorem. We did the square case. You guys are going to watch the video with the cube case. And then this one is like these different weird shapes. It's all based on that. It's completely based on that. When it says how many 5-horse merry-go-rounds are there, that just means non-equivalent, right? That means, okay, if I have 3 blue horses and 1 yellow horse, right? That's obviously not a different merry-go-round if I rotate it, because it's still got 3 blue horses and 1 yellow horse. Anybody would look at that and say, oh, it's the same merry-go-round. It's just been rotated. So even if they don't use the words non-equivalent coloring in the question, that's the common sense interpretation, right? That you would assume that those are intended to be non-equivalent. Then there's one with a baton. A baton is really just a line segment, right? And the ends are being colored. That one's really pretty straightforward. And then these figures that I drew, I'll let you play with that as well. They're not quite as symmetrical as a square, but I think they all have symmetries that you would be expecting, certain rotations and certain reflections. Now, like if you look at A and B, you cannot rotate A and B only by 90 degrees. Because if you rotate by 90 degrees, you're not setting the figure back down on top of itself again, right? So you have to ask yourself, like in part A, the group of symmetries on part A, there's only two. So if I have this figure, so I guess I'm talking through a little bit of this. Just for a second, I've got a couple minutes. If I have this figure, there's, the only symmetry that you have other than the identity where you just pick it up and set it right back down, I can flip it this way. Right? And so you're gonna start thinking, and I guess I said P colors. So, this thing could be any of the P colors. Whatever color paint you put on this vertex though, must be used again here. So I don't have any choices about this vertex. It's gotta be the same. Same thing here, whatever I choose here has to go there. So you'd have P cubed for that. And then of course the identity has P choices for all of them. So there's the answer for 3A. Your summation only has two terms in it because the group of symmetries only has two symmetries to it. Yeah, was there a hand?
Yeah, I may be remembering wrong, but you said there's also like last year that there's like a physical aspect to it. So like kind of like you physically do something to the merry-go-round, like.
Oh, well, yeah, I actually wasn't last year, it was 30 minutes ago. I said, what I said was that you can't flip the merry-go-round upside down. Like if the horses are sitting upright, you can't flip it over as a symmetry because then it's not really a legitimate merry-go-round. So yeah, these free floating figures, as they're called, there's no constraints on like the physical nature of them. Like you can do any, you can reflect it or rotate it as long as it's being replaced back down in the same spot. It counts. So I think the one that you will enjoy is actually the video where you see a three-dimensional one, and I've got a nice colored cube for that. So you'll see the different, there's 24 different symmetries of a cube. And so that's a pretty big group. You've got 24 terms in this Burnside theorem to take a look at. So I'll let you do that. I think the ones on here are really pretty straightforward, and the homework will give you some extra practice with that too. Oh, I just remembered something. I need to take a picture. I meant to stop